Section 1 Introduction. We're going to discuss how we can guide the content generated by advanced language models to adhere to responsible AI principles, such as safety and factuality. This is a challenge because we don't have direct control over the pre-trained representations in these models. There are two main ways to align language models with high reward outcomes, and they differ significantly in how they're applied in the real world. The first is to improve the generator itself, using methods like reinforcement learning, direct preference optimization, and sequence likelihood calibration. These methods adjust the model's weights to align it with a reward model. The second approach is to use add-on solutions at the time of inference, like fudge or cold. These techniques control the output of a frozen model to steer it towards high reward outcomes. We're particularly interested in these inference-time add-on solutions because they leave the base model unchanged. Controlling a language model essentially involves learning a value function that can predict the eventual reward of a given decoding path. In some cases, this value function might be readily available in a rule-based manner, such as lexicographic constraints. However, responsible AI considerations like safety and factuality are generally nuanced and require a data-driven approach to learning the value function. This can be computationally expensive, limiting the number of times the value model can be invoked as autoregressive decoding progresses. This makes tree search algorithms impractical due to latency considerations. In this paper, we focus on methods that only require one call to a controller model per decoding of each token. A common method to control generation from a language model is to sample k candidates and then re-rank them using a reward model to choose the best one. This procedure effectively biases the generation to align it to the reward. However, it's computationally expensive and not suitable for situations that need streaming response generation. Also, the desired trade-off point may require a prohibitively large k, making it impractical to deploy in the real world. We propose a new method called controlled decoding, CD, which increases reward in autoregressive language models subject to a KL constraint. The main ingredient in CD is a prefix scorer for the reward that is used to steer the generation from a partially decoded path. We also propose blockwise CD where control is exerted at every block of M tokens, with no additional training requirements. We decode K blocks of length M, and greedily keep the best according to the prefix scorer, and continue decoding from there. We show that the inference-time add-on control via CD offers significant improvement over existing controlled generation, decoding solutions on the tasks of improving dialogue safety and increasing dialogue length. We also demonstrate that it is possible to change the importance weight of different rewards via tuning a simple knob at inference time. Next, we discuss the KL regularized reinforcement learning setup. Let's consider a prompt, X, and a response, Y, that is a concatenation of T tokens. We use a pre-trained language model, LM, to draw samples in an autoregressive manner. We also have a reward function R, X, Y, that is bounded from above. We only give a reward once decoding has completed and otherwise no reward is assigned to a decoding path. We then define a value function V, X, Y caret, T, that captures the expected cumulative reward of a fully decoded response when decoding continues from Y caret, T. Using the base language model page, we define the advantage function of a decoding policy pi as A, X, Y caret, T, pi. Our goal is to choose pi to deviate from P to achieve a positive advantage over the base policy. We also define the token-wise KL divergence between a decoding policy pi and a frozen base language model P for decoding the next token after X, Y caret, T. Our goal is not to deviate too much from the base policy because that is expected to lead to the degeneration of the language model in other top-line performance metrics. To satisfy these conflicting goals, we use the KL regularized RL objective, which is defined as J, X, Y caret, T, pi, beta. This is a trade-off between the advantage that reward that will be obtained eventually once the response is fully decoded and a language model, LM, negative reward signal penalizing the policy pi for drifting too far from the initial policy page. We let pi caret, star, Z, X, Y caret, T, beta, denote the decoding policy function that maximizes this objective. We are interested in characterizing the trade-off curves achieved by beta in 0, 1 to increase A, X, Y caret, T, pi, at the cost of an increased KL penalty, D, X, Y caret, T, pi. Our main result in this section is the characterization of pi caret star. The optimal policy for the RL objective is given by pi caret star z x y caret t beta proportional to p z x y caret t e caret frac 1 beta gamma beta v x y caret t z. This result resembles that of previous work, with the main difference being the controller is token-wise here. Our goal is to develop an inference-time alignment solution that keeps the language model frozen. This theorem gives us a way to do that by combining logits from a frozen LM and those of a value function. Section Summary. In this section, the authors discuss the challenge of guiding machine-generated content to adhere to responsible AI principles, such as safety and factuality, in generative language models. They propose controlled decoding, CD, an alignment mechanism that increases reward in autoregressive language models while subject to a KL constraint. CD utilizes a prefix scorer for the reward to steer the generation from a partially decoded path, and it can be learned in an off-policy manner using the Bellman update. The authors demonstrate that CD offers significant improvement over existing controlled generation solutions in tasks such as improving dialogue safety and increasing dialogue length. Section 3. Proposed method. Controlled decoding, CD. We're proposing a method called controlled decoding, CD. This method is based on a theorem that provides a solution to the KL regularized RL problem. However, this solution requires access to a value function, which we call a prefix scorer, as it's used to score different decoding paths. This prefix scorer is defined by a Bellman identity, which is a mathematical relationship that describes the value of a state in terms of the expected future rewards. To train this prefix scorer, we use a transformer network, a type of neural network that's good at handling sequential data. This network is parameterized by weights, which we denote as W. We use a loss function, which measures the difference between the predicted and actual values, to optimize these weights. This loss function is inspired by the policy evaluation updates in DQN, a type of reinforcement learning algorithm. The training process for the prefix scorer can be performed over an off-policy dataset, which is a dataset that's not directly related to the current policy. This dataset is scored offline using the reward for all possible combinations of inputs and outputs. However, this training process requires access to the base language model to compute the targets. In contrast, we propose using fudge, a method that replaces the supervision through the Bellman identity with the eventual reward from the decoding path. This method can provide an unbiased estimate of the value if the dataset for training the prefix scorer is collected on policy, meaning it's directly related to the current policy. To speed up the convergence, we can use fudge to supervise the initial iterations of the training before switching to the DQN-style policy evaluation updates. Once we have the prefix scorer, we can use it in two different ways at inference time. The first way is token-wise sampling, where we use the prefix scorer to sample tokens one at a time. The second way is blockwise sampling and re-ranking, where we use the prefix scorer to score blocks of tokens and then choose the block with the highest score. This method is similar to the best of K strategy, but it only needs to decode M tokens at a time, whereas the best of K method needs to fully decode all K sequences before it can select one. Section Summary. The proposed method, controlled decoding, CD, introduces a prefix scorer, which is a transformer network trained to approximate the value function used in RL. The prefix scorer can be used for token-wise sampling, where it downweights decoding of tokens that may lead to undesirable outcomes, and for blockwise sample and re-rank, where it re-ranks decoding paths based on the prefix score. This method improves language model alignment and reduces inference latency compared to existing strategies. Section 4. Experimental results. We conducted our experiments on the DSTC-8 conversations corpus, using the POM2XXS model as our base. We also trained our prefix scorer models with the same base model. For evaluation purposes, we trained a larger model, POM2XS. We compared our results with three baseline models: Fudge, KL regularized PPO, and Best of K. Fudge was trained similarly to CD, but instead of using the target in the equation, we used the explicit reward from a given decoding path in the dataset. We also considered a variant of Fudge, called blockwise Fudge, which was inspired by the blockwise CD method proposed in this paper. We evaluated our models based on trade-off curves for expected reward or win rate over base policy versus the KL divergence between the aligned policy and the base. A method that increases the expected reward with the smallest sacrifice in KL divergence is considered more desirable. For CD and fudge, we adjusted the strength of the prefix score to achieve trade-off curves between performance and KL divergence. For PPO, we adjusted the strength of the KL regularizer to achieve the same goal. For best of K, blockwise CD, and blockwise fudge, we did this by adjusting K in our first experiment. We used the response length as the reward to mitigate the effect of reward overoptimization. We found that best of K achieved a better reward KL trade-off compared to KL regularized PPO. We also found that token-wise control using both fudge and CD led to a more favorable reward KL trade-off compared to KL regularized RL. When we considered blockwise control, we saw a significant difference between the behavior of blockwise fudge and blockwise CD, with blockwise CD performing on par with best of K. In our second experiment, we aimed to improve the safety of the responses in conversations. We trained two independent reward models on the side-by-side safety signal using POM2XXS and POM2XS. The goal was to generate safe responses in a dialogue setting. We found that token-wise controllers didn't offer much safety improvement over baselines, whereas blockwise CD and fudge offered a substantial improvement. However, neither method was able to match best of K. In our third experiment, we combined the safety and length prefix scores to simultaneously improve safety and increase dialogue length. We found that with a neutral length reward, the dialogue length of blockwise CD remained mostly constant. However, best of K with no dialogue length reward increased the dialogue length around 3x. Introducing a positive length reward resulted in increasing dialogue length for both blockwise CD and best of K, but the increase in length for blockwise CD was more modest. This came at the expense of a decline in dialogue safety win rate. In conclusion, our experiments showed promising results, but there is still room for improvement and further investigation. Section Summary. The experimental results section presents the dataset, models, baselines, and evaluation metrics used in the study. In Experiment 1, the goal is to increase dialogue response length, and best of K achieves a better reward KL trade-off compared to KL regularized PPO. In Experiment 2, the focus is on improving dialogue safety, and blockwise CD and fudge offer substantial safety improvement, but neither method matches best of K. In Experiment 3, the aim is to simultaneously improve dialogue safety and increase dialogue length, and blockwise CD shows a more modest increase in length compared to best of K, but at the expense of a decline in dialogue safety win rate. Section 5. Related work. In this section, we'll discuss related work in the field. Firstly, we'll look at controlled decoding. Fudge discovered that decoding with a specific constraint could be achieved using a prefix score, which is a tool that uses Bayes' rule. They also improved the training data to train this prefix score. Director took this a step further by demonstrating that the prefix score could be learned in conjunction with the language model itself, which would result in faster inference times. Getty suggested training separate networks for positive and negative scoring, which could then be combined to get a prefix score. However, our approach differs from these. We provide a thorough demonstration that the prefix score should be trained as the value function for the decoding policy of the language model. This approach allows us to make significant improvements over the existing work. Our work also has similarities with rule-based control. This involves using a tree search with a heuristic to determine the quality of a decoding path and guide the decoding towards favorable outcomes. Another method explored is gradient-based sampling using Langevin dynamics, which performs significantly better than sampling without gradients. Next, we'll discuss reinforcement learning, RL, another relevant field. This involves learning with a KL penalty in the language model. It was observed that reinforcement learning with a KL penalty could be viewed in a Bayesian manner with a corresponding reward function. However, the full connection in an autoregressive decoding setting was not made, which is what we contribute in this work through CD using a variant of the Bellman update similar to DeepQ learning, DQN. Another work closely related to ours is one that designs a value-based offline algorithm, but with a different learning objective than ours. Other related RL work includes improving generators through on-policy RL. Sparrow demonstrated that a variant of proximal policy optimization, PPO, with an additional language model regularizer is effective at various safety objectives and aligning with human preference. Lastly, we'll discuss supervised learning from negative examples. This is another related field that involves improving generators through supervised interventions. These interventions include unlikelihood training, contrastive losses, and direct preference optimization. Unlike our work, these methods are all used during training, but they could similarly be used to increase the likelihood of positive examples by decreasing the likelihood of negative ones.